Okay, okay, now it's working. Okay,
Floor is all yours.
okay, yeah. Thanks for the introduction. So next I will share with everyone our work on MAGIS, memory optimization by coordinated graph transformation and scheduling for DN. The first author of this paper, Renze Chen, is my PhD student. Unfortunately, he cannot come due to visa problem. I will first introduce the motivation, followed by the techniques and the evaluation results. So memory pressure is a critical concern for today's DNNs. One source of this memory pressure comes from this larger tensor size. So if you see the recent model, they often hold billions of parameters. Another source is this large data. So the data size continues to increase. And the recent these large language models, they provide text length in thousands. Okay, so another source of this memory pressure comes from this long lifetime of tensors. For example, for this training graph, and the computation, the activation computed need to resolve in the memory until it is used in the backward parts. And for some other network like this DenseNet, UNet, and the diffusion, they often use these long skip connections. So the tensor has to reside in the memory until it is used. In general, there are two kinds of technique to optimize the memory for DNNs. One is this model compression, including pruning, quantization, decomposition, which try to compress the tensor size at the cost of the model accuracy. Another technique is called graph scheduling, including reordering, rematerialization, swapping, which try to reduce the peak memory usage by managing these tensor lifetimes. And the goal of this work is to optimize the memory, is to reduce the peak memory usage. Okay, so the graph scheduling, there are different techniques. One is this reordering, which try to reduce this peak memory usage by permutating the computation sequence. Another technique is called this rematerialization. It will discuss the tensor in between and recompute them when needed. So this will also help to reduce the peak memory usage. The last one is called swapping. We will temporarily swap certain data out and swap the data in when needed. Okay, so for this reordering, in general, it doesn't hurt this latency. It optimizes memory only. But for the last two, this rematerialization and swapping, we will treat this latency for memory. As you can see, the latency is increased due to the overhead of this recomputation and additional data transfer. So this graph scheduling I just presented, they only affect the tensor lifetimes. Another technique is called graph transformation. We can mutate the tensor structure and the tensor size. So there are two categories of this graph transformation. The first one is interim transformation, which is based on certain algebraic properties. Another one is called this aggregation transformation, which try to merge this small operator into a larger one. And the goal is to improve these hardware utilizations. Okay, we find that actually this aggregation transformation is very effective. In this case, actually, it can reduce this latency, but at the same time, actually increase this peak memory usage. In this case, the peak memory usage is increased from 2 to 5. So it treats this memory for latency. Okay, so we introduced the dual of this aggregation or the reverse of this aggregation, which means we try to split some operator into multiple smaller one. Okay, we call this as efficient transformation. So in this case, you can see actually this efficient transformation, of course, then the latency gets worse because this lower hardware utilization, but the peak memory usage actually is reduced from 5 to 2.5 in this case. So we can treat the latency for memory. So the goal of this paper is by putting this efficient transformation, graph transformation, and this graph scheduling all together, we can have this extend this memory and the latency design space trade-off, enhancing the capability of graph scheduling for memory optimizations. And next, I will introduce the techniques. So the framework is called MAGIS. MAGIS tries to optimize memory and latency under a given latency memory constraint. There are four components: front end, analyzer, optimizer, and backend. The front end will pass the user input and generate a graph intermediate representation. That is the input of this analyzer. Then analyzer will build the optimization space for the Fission transformation. And meanwhile, we will generate this initial search state. Then the optimizer will iteratively apply the transformation, schedule the transformed graph, and in the end generate optimized graph and schedule, which is used as input of this backend. The backend will generate the executable code compatible with the existing frameworks such as PyTorch and other frameworks. Okay, so before I introduce the analyzer, we first need to define a Fission transformation. But we need to represent this graph level dimension first. Okay, so for each operator, in this case, it is MATMAL. And given the tensor expressions, then we can derive these dimension mappings. So in this case, this green square represent the mapping for this spatial dimension, and this hollow square represent the mapping for the reduced dimension. Then you can do this dimension mapping for each operator that will give you the dimension graph, dimension for the entire dimension graph. Okay, next I will define this Fission transformation definition formally. So it's for SDN. It means we will split this subgraph S along dimension graph D into n parts. Okay, let me use this example to explain. So given this graph, now we want to split this subgraph S consists of nodes 3 to 8. Okay, then these nodes 0, 1, 2 are inputs. Then we want to use this dimension B as the split dimension, and we want to split into 2 parts. Okay, so then because these 0 and 2 have dimension in D, so they have to be sliced, and we introduce this slice operator. And this dimension 1 has no dimension in D, so it can be shared. And for the outputs, this 6 and 7 has spatial dimension in D, so it has to be merged, and we introduce this concatenate operator. And this 8 actually has, node 8 has this reduced dimension, so it needs to be summed up. And this graph complexity actually grows after applying this Fission transformation. Then we propose a data structure to record only the transformation itself without directly rewriting the graph. So for example, in this case, we have 4 subgraph S1 to S4. Instead of rewriting the graph, we just propose this data structure called Fission hierarchy tree to record the transformations. And ideally, actually, every subgraph can be a candidate for this Fission transformation. And we propose a performance metric called this score to estimate the minimal peak memory reduction after splitting this into 2 parts. And in this case, the heat S represents the peak memory contribution, and the input S is the total memory of the input. Okay, next, we will construct a Fission hierarchy tree. It works like this. First, we recognize the memory hotspot in the graph. Then construct the dominator tree of the graph, then compute the score of the subgraph dominated of each node, then select the subgraph with the largest score in different intervals, and finally we can construct the initial Fission tree. So this example then to show you that actually we don't need to physically change the graph, we just need to use this Fission hierarchical tree to record all the transformations. And next I will give you an overview of this optimizer. It works in this way. So given a graph, we will apply certain rules. Then it will generate a new graph. Then we apply this graph scheduling. Then we pick some good performance graph into the queue. Then we do the next run. If we do in this way, actually, this graph scheduling is frequently called. And also the graph transformation and scheduling, they are multi-objective optimization. So this process actually is very complicated. And we want to simplify the graph scheduling process a little bit. We observe that this graph scheduling, including this rematerialization and the swapping, we can be decoupled into graph transformation and reordering. For example, this rematerialization, we can, in this case, it can be decoupled into graph transformation with introducing a new computation for B and also reorder the B and E. Okay, so this will achieve the same result as this rematerialization. Similarly for this swapping, right? So in this case, actually, we can do a graph transformation by introducing this load and store. Then we will do a reordering. This will achieve the same effect as this swapping. Okay, and then after that, then we can have a unified design space trade-off. Then each transformation rule makes a small step trade-off for memory and latency. And now this graph, this scheduling focus on optimizing memory without any trade-off. And actually, we further propose incrementally scheduling technique to keep the overhead low. We just it's based on the previous schedule and newly mutate subgraph. Okay, now next I will present this evaluation result. So we try on 2 platforms, compare with 6 baseline, and we try 7 networks. First, for the latency result, okay, given a latency overhead less than 10%, so MAGIS, the peak memory usage is only 15 to 85% of the baseline. If we set the latency overhead to 5%, the peak memory usage is only 25 to 80% of the baseline. Okay, on the other hand, we also can change the memory ratio, right? So if we set the peak memory ratio to 80%, the MAGIS only, the overhead of MAGIS is less than 5%. But the baseline actually can go as much as 40%, even failed for certain cases. If we set this peak memory ratio to 40%, MAGIS only incur 15% latency overhead, but for the other baseline, actually, they can incur at most as 70% overhead and failed for certain cases. Okay, to summarize, MAGIS we propose this MAGIS is a framework to optimize this DN memory by the coordination of graph transformation. In particular, we introduce a new transformation, coefficient transformation, and graph scheduling. And the result is MAGIS use only 15 to 85% of the peak memory usage compared to the SOTA-works under the same latency constraint. And this project is open source. You can find on my website. Thanks for your listening.
Hey, thanks for the great talk. Any questions from the audience? Yeah, please.
Okay. Hi. Thank you. Good talk. So I'm Gonghan from Stanford. I have a question now. Do you have a performance model for your optimization? So you said budget for the latency. So how do you model the latency?
Right. So we propose this. This is the performance model is this score. Let me go back. Yes. So this S is the subgraph we use. We select for this split. Right. So then we use this score S. But this is just a rough estimation. So we only estimate how memory saving we can get.
So you only use the flops to approximate the latency, or you only measure, only model?
Oh, okay. For the latency, actually, is done by profiling. But this is a model for the memory saving.
Oh, okay. Okay. Thank you.
Any other questions?
Yeah, so nice talk. So one question I have is that I think for rematerialization and swapping, essentially that's introduced new operators to the graph, and that also creates a infinitely large search space because you can actually do rematerialization.
Right.
And so how do you navigate the search? What are the algorithms and the optimizations applied to prune some search space? Because you don't want to apply many.
Right. Yeah, that's a good question. Actually, we have some heuristic to. Okay. Yes. Yeah, you're right. So we have some heuristic to reduce the search space. I think I talk about the details. So actually, we set a certain threshold to control the search space not too large. Yeah. Okay.
Hey, maybe we have time for one more questions. If not, let's thank the speaker once again. So our next presenter is Jeffrey Yu. He is a first-year PhD student at Stanford. So it's very impressive that he already has a first author paper at ASPLOS. He's going to talk about 8-bit transformers and edge accelerators.
Okay, thanks. Hello, everyone. My name is Jeffrey, and today I'm excited to show you our work on 8-bit transformer inference and fine-tuning for edge accelerators. Transformer models have achieved state-of-the-art performance on natural language processing and vision tasks. For example, the BERT and GP models have revolutionized language understanding and text generation. On the other hand, Vision Transformer has outperformed convolutional neural network on various image processing tasks. With increasing application of transformer network, there's a strong motivation to bring them onto edge, as they offer better privacy, latency, and energy efficiency through custom accelerator. However, transformer models are large, and they require heavy computation and memory resources. Quantization is a promising way to reduce the resource required by transformer network. And recently, there has been strong interest around using 8-bit data type for inference and fine-tuning. Prior work has quantized transformer network to 8-bit integer. However, they mainly target inference and only quantize computation-heavy gem operation. And they require additional techniques to maintain accuracy. QLoRa is a work that quantizes the pre-trained model into 4-bit norm float to reduce the model storage, but the operations are still carried out in floating point formats. NVIDIA has proposed FPA for both inference and training, but they also only quantize the gem operation. So in this work, we explore and we perform an in-depth analysis of two data types, POSIT-8 and FP8. We support both inference and training, and we're quantizing all transformer operations. Also, we only use operator fusion for inference and potential scaling for backward pass. Now I will introduce the two data types we use in this work. First of all, NVIDIA's FP8 comes with two formats, E4M3 and E5M2. They both have fixed width exponent and fraction fields. E4M3 has more precision and less range, and it can be used for both forward and backward pass. E5M2 has a wider range and is only used to store activation gradients during the backward pass. POSIT had two configurations, the total number of bits and the number of exponent bits. In this work, we're using 8-bit POSIT with one exponent bit. Different from FP8, POSIT has an additional field called regime, and the length of the regime is determined by the scale of the number. Regime make the exponent and fraction fields both variable length. Therefore, numbers can use all the bits for exponent to represent very large or very small numbers, like the first and second examples on the right. For values around 1, numbers can also allocate most bits for fraction fields. We have a more precise representation of the value. Because all the fields are variable length, POSIT needs to be decoded before each computation and encoded back into POSIT format after the computation. If we compare POSIT with FP8, POSIT can represent much larger number, like 4096, compared to E4M3 can only represent 448. It can also represent smaller number than E4M3. For values around 1, POSIT has one more fraction bit than E4M3 and 2 more fraction bits than E5M2. Since most of the values are normally distributed between 0 and 1 in neural network, this property of decreasing precision as the value moves away from 1 is favorable for representing neural network data. POSIT also has some interesting properties which allow us to build more efficient softmax. POSIT can approximate reciprocal function by flipping all the bits except the sign bit, and it can also approximate Z-point function by inverting the sign bit and shift all the bits to the right by 2. We can then do some transformation to build exponential function. These two properties allow us to perform softmax operation using only bitwise operation and subtraction operation so that we can get rid of the bulky divider and exponential unit on the chip. Now I'll introduce the 8-bit transformer inference. First of all, different from prior work, we quantize all transformer operations beyond matrix multiplication. For example, we're quantizing attention scaling, softmax, layer normalization, activation, and residual addition. We perform operator fusion, meaning performing LMOS operation in conjunction with preceding gem operation without rounding or writing back to memory to mitigate accuracy loss from quantization error. Here we show the post-training quantization accuracy or F1 score of BERT models on squat question answering tasks. And the numbers marked in green is within 1% loss compared to B416 baseline. As you can see, we achieved within 1% accuracy loss through just operator fusion with no scaling factors. And we also observed that smaller models are harder to quantize. For example, for mobile BERT models, we need to fuse all the operations in order to achieve within 1% accuracy loss. Whereas for larger models like BERT models, we can quantize all the operation while still achieving on-par accuracy as B416. We also evaluated on the Whisper model an encoder-decoder-based transformer model on the speech recognition task. And similar to BERT, we observed the same pattern that smaller models are harder to quantize and have larger performance degradation. For Whisper Tiny, posit A1 suffered to reach the desired accuracy, even through operator fusion. Through inspecting tensor value distribution, we found that Whisper Tiny has wider activation distribution. So we tested another posit configuration, 8-bit posit with 2 exponent bit, which has even more dynamic range, and we found it performs better. It means that the range is favored over precision in this case. Lastly, we tested on the large language model, and we found that posit A performs better than FPA on large language models. It's mainly because Llama 2 activation have outliers values in some of the channels, and posit A can better represent these outliers because of its very large dynamic range, and therefore has better perplexity. To summarize, both posit A and FPA shows post-training quantization accuracy on par with B416. However, certain data types may perform better than another, depending on the specific workloads. So the selection of appropriate data type should be tailored to the specific models and associated tasks. And now I will introduce 8-bit fine-tuning. Different from prior FPA work, which only quantized the input to gem operation and left most of the intermediates in 16-bit format. In this work, we quantize all the operation, and we save all the intermediates in 8-bit. Transitioning intermediate output to 8-bit format will be beneficial for memory-constrained edge devices. While quantizing activation in ways to 8-bit doesn't require any scaling factor, this could be tricky for some of the intermediates like activation gradients, because it is dominated by small values. And in this case, we have to apply scaling to move it into 8-bit representable range. And we use delay scaling, same as NVIDIA's FP8, meaning computing scaling factor using historical gradients statistics so that we only need to do one pass of the data. We also apply low-rank adaptation to further reduce the fine-tuning memory, where we reduce the number of trainable parameters by injecting low-rank parameters, and they can be merged with pre-trained weights during inference to reduce latency. Lower by default enables 8-bit fine-tuning because the pre-trained weights are intact during the training. However, previous methods perform lower matrix multiplying 16 bits and dequantize the pre-trained weights before performing linear operation with inputs. Our methods improve upon the 8-bit lower by quantizing both the lower weights and the merged weights, so that we keep everything in 8 bits during training. Also, there is no accuracy loss because everything's 8-bit. So similar to quantization aware training, this guarantees that we don't need to re-quantize the model after we merge the weights. To find together, these techniques, lower plus 8-bit quantization, can reduce fine-tuning memory by more than 3 times. We perform our fine-tuning experiments on mobile bird and robotic models, and we run them on glue and squat question answering tasks. And we found that both posit A and FPA can achieve accuracy on par with B416, and also our approximated softmax show no adverse effect on training performance. We also evaluated how posit and FPA performs in an neural network accelerator. To do this, we designed an accelerator using high-level synthesis. We synthesized the design using 40 nanometer technology at 200 megahertz. The accelerator consists of an n-by-n systolic array with an n-wide vector unit to perform the nonlinear and reduction operation. Also, for posit A accelerator, it requires additional encoders and decoders because all the fields are variable length. So look at the single MAC unit. Both posit A and FPA are much better than B416 with on average 50% error reduction and 60% power consumption reduction. However, we found that NA is still much better than posit A and FP8, meaning that for inference-only workloads, NA is still favorable. Also, posit encoder and decoder is less than 20% of a single MAC, so they're negligible in terms of the total accelerator. In terms of vector unit, well, the posit approximation has significantly reduced the reciprocal and exponential unit area and power. For example, the posit 16 reciprocal unit is 85% smaller and reduced power by 75%. And the exponential unit is 62% smaller and reduced power by 42%. If we look at the total accelerator, both posit A and FP8 can reduce area by 30 and 34%, and power by 26 and 32%. And if we compare posit A with FP8, we found that posit A has a smaller vector unit because the use of the posit approximation. However, in terms of total accelerator, FPA is still smaller because the map of FPA is smaller, since FPA has one less fraction bit. To conclude, in this work, we perform full 8-bit transformer inference and fine-tuning using 2 data types, posit A and FP8. And we apply operator fusion to mitigate the quantization accuracy loss. We use an improved 8-bit lower with 8-bit gem operation. we also designed an error and power efficient posit softmax. And we found that both posit A and FPA emerge as robust solution for conducting transformer inference and fine-tuning on edge accelerators, offering improved hardware efficiency with minimal accuracy compromise. Thank you.
Okay, any questions from the audience? Yep.
Hello, I am from EPFL. Thank you for the great talk. So I was just wondering, recently Microsoft has also introduced some scaled number formats, which they call like microscale number formats. Do you have any insights as to how that would compare with FP8 and POSIT-8?
Yeah, so right now they're doing microscaling mainly with even lower precision data type, like maybe 4-bit. However, I think they're mainly targeting inference as well. So since these data type doesn't have the range for training, so in terms of inference only, microscaling might have some advantage over POSIT A and FPA. And we think that for POSIT A and FPA, they're mainly like a general purpose data type for conducting training and inference.
Okay, thank you.
We have enough time for some more questions. Any other questions? Actually, I have one question. So you mainly talked about edge accelerators and small models running on the edge device, I guess. But large language models can also benefit significantly by being compressed and running on single hardware instead of being distributed. Do you see this to naturally scale to large language models as well?
Yeah, this is a great question. So in this work, we only explored quantizing the large language model for inference, but yes, the large language model will also benefit from this API quantization. And I believe that we didn't do this for pre-training, but I believe that they both data type has the capability of performing pre-training using like entirely in this API as well, I think.
Okay, thank you. Any other questions? Oh.
For enhancing the hardware efficiency, if you reduce the bit width of an accumulator, that might lead to a degradation in accuracy.
Oh,
right?
Sorry, can you speak?
Hello. Yeah. So in order to enhance the efficiency, you will be reducing the accumulator bit width, right? It might lead to an degradation in the accuracy. How are you encountering that? Like, what's the degradation in the accuracy also?
So since we have this customizable accelerator, we have experimented accumulating in 16 bits, and then we do see some degradation. We do see some degradation, like maybe around 1 to 2% if we do post-training quantization without retraining. However, this part of the accuracy loss can be regained from training the model using 16 bits, like training the model using accumulations data type as 16 bits.
Are you anyway regaining that accuracy, or like that's fine when your final model has got degraded accuracy?
Sorry.
Like, is there any way, like, are you regaining that 2% accuracy, or like your final model has got original model accuracy with some degradation? Yeah. Oh, okay, thank you.
Hey, let's thank the speaker again. And our next speaker is Sanhong Tan. He's a PhD student from Peking University. He's going to talk about his work, Cocco, on hardware mapping co-exploration for memory capacity and communication.
Chengrui is layer by layer. We need to even have your application of the top. The layer fusion can release the burden by building the layer graph, as known as the in this way, the information data can be used on chip for subsequent layers, using the IO communication. Before the layer fusion protecting hardware, some studies have proposed dedicated pipelines. However, they mainly focus on chip specific structure for arbitrary topologies, when the larger oxygen battery, you can buffer. However, larger battery or layer zero, and additional that rate time, we also better.
Hey, thanks for the great talk. Any questions from the audience? Okay, I have one question, which is it seems like you studied a lot of CNNs, and in the slides I also saw like some transformers and stuff. Is there like a certain model architecture where your technique will be more useful or less useful? Is there like any insight that you had from the study? So my question was, it seemed like most of the evaluation focused on CNNs. So I was wondering whether CNNs were more effective, or was that just like not exactly the reason? Yeah.
Hopefully, we study the bottleneck of the intermediate data and specific for the heat inference and the deep, such as the heat series scenario, when the acceleration is very bottleneck. And so most of our background for the Liang. However, our graph partition and the memory physical correlation can also practical with the transformer model. So we also related some results of the graph partition in the transformer model to also work. Okay.
Thanks. Are there any other questions from the audience? If not, let's thank the speaker once again. So our last speaker is Christiana Gianola. She's a postdoc at University of Toronto. Today she's going to talk about Atlanta, compression technique for machine learning. So
Thanks for the introduction. Hi, everyone. I will be presenting our work at Atlanta. A quick note on the presentation. One of my co-authors was planning to give the presentation today, but he is not able to present it because of an emergency issue. So please forgive me. I will try to do my best to present the paper. So this project is a collaborative effort, and I'm here to represent our group, and especially Alberto, who is the lead author of this project. Our work targets the significant energy and latency costs associated with communication in typical systems. Going off chip in such system can consume up to 100 times more energy and can be 50 times slower compared to on-chip memory usage. Atalanta operates just before the off-chip memory controller, compressing fixed-point data for off-chip storage and transfer, which reduces the associated costs. Atalanta is optimized for machine learning workloads, functioning both for inference and training, and it is successfully evaluated across a wide range of deep learning models, including transformers, image classification, object detection, and recommendation systems. Atalanta is lossless, which means that the data you put is exactly the data that we can get after the compression and the compression process. And this guarantees that the performance of your task remains untouched, like the accuracy in the classification task. Atalanta is programmer transparent technique, and the low-level driver manages the data transfers discretely. And finally, Atalanta provides high compression efficiency. On average, it reduces the size of the weights to 60% and activation to 48% of their original volume. This is translates to directly significant cost savings and improved efficiency. Atalanta comes with low cost. It incorporates just tiny additional hardware units, which hardly affect the overall energy consumption and resources. So let's see in more detail the key idea and the software and hardware components of Atalanta and the evaluation. In this problem, we are working with fixed point data, and our goal is to find an effective way to compress this data that does not only offer high compression, but also comes at low cost. We handle two types of data: the weights, where the distribution is already known, and aggregations, for which we can perform profiling by running multiple examples to obtain a representative distribution. Once we know this distribution, the next step is to find the most efficient way to compress our fixed point data. Historically, we have seen a lot of various compression algorithms, like the arithmetic coding, which has been a very efficient data compression approach from the 1980s. It is known to be very efficient across a wide range of data values in case that we know the distribution of the data values in advance. So I will quickly revisit some basic stuff on arithmetic coding. Arithmetic coding takes an entire sequence of data samples, in this case, the values of an intake data tensor, and transforms them to a single real number. The number of bits required to represent the sequence depends on the sequence length or the number of elements in the tensor and the frequency of each element. And for simplicity, let's consider an int2 tensor as an example. An int2 tensor has four possible values or symbols from S0 to S3, and arithmetic coding begins by identifying the probability of each symbol in our sequence. Then, based on these probabilities, each symbol is assigned a corresponding range on the number line between 0 and 1. The encoding process is then done sequentially by choosing a symbol and dividing each range into new subranges. Each symbol in the sequence progressively narrows down to the corresponding range, and this process continues progressively for all tensor values until we reach a final range that represents the entire sequence of the symbols. Arithmetic coding provides a near optimal compression. However, it comes with many challenges when it comes to implement this algorithm on the hardware level. There are three key challenges. First, to operate arithmetic coding constantly needs to access the probability tables that track each symbol and its frequency. For an intake data type, the table has 256 entries, one for every possible value, and maintaining and looking up for this table is not only space consuming, but also it's very power intensive. And in fact, in a typical setup, this can consume as much as 93% of the DRAM power. Moving on the second challenge, as we encode symbols, the precision needed increases because our range keeps getting smaller. And as a result, the algorithm requires very costly arithmetic operations, such as wide multiplications and division. These consume more energy, increase the latency, and require large secrets, which make this design unfavorable to be implemented in hardware. And lastly, arithmetic coding is inherently sequential, which may not align with the parallel processing demands of our machine learning workload. And this sequential nature limits its encoding and decoding rates, and it might generate only 1 bit per cycle in the base implementation. So to resolve these challenges, we have designed a Atalanta that provides near optimal efficiency, and it's also practical through different techniques. First, Atalanta partitions the value space into sub-ranges of values, sharing a common base with each value represented as base plus an offset. For an int-8 data type, this can be 3 bits for the base and 5 bits for the offsets. Atalanta then applies the arithmetic coding algorithm only for the base part, while storing the offsets directly as they are. This lowers the number of entries at the probability table from 206 to 890. Why does this work? Basically, if we have a certain value distribution like this, in case of the weight tensor, arithmetic coding can make use of different frequencies and efficiently compress them. And if we divide it into 8 sub-ranges for 3-bit base, the distribution of the bases will closely mirror the original value, the original data distribution. However, for the offsets, they are left with at least 5 bits per value. So this is an issue that we need to address, and I will describe more details next. Before that, at a high level, the Atalanta has 2 key components, a software profiler and hardware module. The profiler pre-analyzes data prior to runtime, supplying the hardware module with some statistics and values that require during the runtime. So what does the profiler do? It takes a weight or activating tensor and generates a histogram of value. And then Atalanta runs a simple algorithm to search for the sub-ranges iteratively. And it basically says, if I'm going to encode numbers as base plus offset, with offset stored directly, find me the sub-ranges that lower the total footprint with sub-ranges that are not necessarily equal. And the idea is that the values that are very frequent, like the ones that we see here, they can be assigned with a very short ranges, so they have very few offset bits, as they contribute more significantly to the overall data footprint. And the opposite part, the values that are infrequent, they have a larger range, so they have more offset bits. After grouping figured out the sub-ranges, probability table is created, and this for each sub-range, and the minimum value is stored in 8 bits. The number of offset bits is stored in 3 bits, and the probability limit that indicates the sub-range frequency is stored in 10 bits. In our experiment, we find that 3 or 4 bits for index were enough so that bit tables in total have 8 or 16 entries in most of the cases. And then we have the hardware component of Atalanta. The probability table, along with other storage elements, requires a storage that is less than 50 bytes per instance. And the rest is a small unit that has some combinatorial logic. For more details on our hardware, please read our paper. So going into the evaluation part, we compare Atalanta to 2 different classes of compression algorithms, the widely used powerful LGMA algorithm. This algorithm is very powerful compression schemes, but they are very expensive to be implemented in hardware. And the second class of algorithms is the hardware-friendly bit length compression algorithm. We evaluate these 3 across a wide range of deep learning models, including Llama 2, GPT-2, and also some video models. Starting with the wave compression measured by the relative footprint in the y-axis across different models in the x-axis, Atalanta outperforms bit-plane compression for all models, with the highest difference of 35% shown for the GPT-2 model and the lowest difference of 9% shown for the GPT model. When compared to one of the LTMA configurations, Atalanta matches its compression performance for the resting 50 model and outperforms it for all other models with a maximum of 37% memory reduction. For activations, a big plane outperforms Atalanta in resting 50 by 5%, while Atalanta performs big plane compression in all other models, including transformer models, with a maximum of 15% extra reduction. Compared to the same LVMA configuration, but for activations, LVMA slightly outperforms Atalanta for visual models and GPT model, with a maximum difference of 7% in footprint reduction, while Atalanta outperforms the Llama 2, outperforms the LVMA configuration for the Llama 2 model by 6%. In hardware, Atalanta can be seamlessly integrated with deep learning accelerators at low cost. And when integrated with the tensor core-based accelerator, Atalanta improves the performance and energy efficiency by 1.44% and 1.37% times respectively. Atalanta can also reduce the data footprint while training for 6-point data. Training activations are temporarily stored in non-stick memory during the forward pass and then retrieved for the grading calculations during the backward pass. Atalanta compresses the weights and activations before sending them to the memory and decompresses them when they are retrieved for processing. The nature of training data is different as both weight and activation distribution continue to change across training epoch. For our experiment with ResNet 18, Atalanta generates probability tables at distant epoch starting at epoch 0, 35, and 65. Every table is used until the other one is generated and we measure the relative footprint at different times. The measurement at epoch 3 shows a relative footprint of 56%. At epoch 35 shows a relative footprint of 70%. And as the training continues, we have a relative footprint of around 40%. To conclude, Atalanta is a low-speed hardware software for design compression engine that lowers the communication footprint for both fixed-point inference and training. It has low hardware cost and high energy efficiency. It is also programmer transparent and can be seamlessly integrated with any AI accelerator. Thank you, and I'm happy to take questions.
Any questions from the audience?
Hi, Christina. This is Erasmus from the University of Illinois Maeng. Great talk. Thank you so much. And my question is, how does Atalanta interact with lower bit quantization?
Okay, thank you for the question. Overall, we find that compression approaches, they are orthogonal and they can play upon quantized models. So we can quantize model in very low precision, either for rate feeds, and we can apply Atalanta upon them to further reduce the memory footprint. We compare our work with two popular quantization methods in the paper, and we saw that we have around 2 to 5% memory footprint reduction upon them.
Any other questions?
The question is that Atlanta will be getting because we have been using big fonts.
Yeah, it's only work for fixed point.
And the if I'm doing a GQ, this is the kind of back. That I can look all complex these images by GQ.
Yeah, I think so. Absolutely. Yeah.
We have time for more questions. I'll check into them. I have one question. So it seems like you're using model mainly because of the data type. At one point, we'll actually look from the view. If I wanted it for like, for example, Bitcoin.
Yeah, I think that it would be slightly worse in terms of the area overhead. But we probably need to change the subreddit dynamically to cover it. And I think that it will have like a similarly high performance energy benefits, but with a bit larger area.
Thank you. Let's thank the speaker. Hey, and that's the end of this session. Thank you for attending.
Thanks. Yeah.